Performance analysis of cascade by adaptive filtering based on normalized orthogonal gradient adaptive algorithm is topic. Outline of this presentation, including introduction, contribution of this work, proposed algorithm, and experiment result conclusion. For introduction, for this idea, according to practical situation, nonlinear adaptive filtering now involved to guarantee for many fields of the real-world application as stated in linear, nonlinear architecture based on binary model. Spline-based adaptive filtering or SAF architecture consists of linear adaptive filtering connect with adaptive lookup table for non-linear adaptive filtering adapted by spline-based interpolation. Now, SAF has been investigated to against impulsive or color noise with many research such as safe-based architecture has been analyzed in the convergence properties or by adaptive step-size mechanism or based on Hammerstein function. We call Hammerstein-based SAF has been derived by a non-linear model to implement block-oriented. And then generally trouble in nonlinear system, there is no a priori or previous information used. So that means we set up a set of cascade of linear and nonlinear model has been introduced to identify the best solution with the present informed in the real world environment. So as stated in many previous research, the cascade SAF, or we call CSAF, consists of a linear connect with nonlinear tree box and or linear tree box cascaded with least mean square algorithm that has been proposed in the system identified. And many research in engineering have introduced. The contribution of this work is to derive CSAF cascade spline adaptive filtering model by using NOGA is normalized orthogonal gradient adaptive mechanism under the minimized cost function or stochastic gradient-based approach. To the best of our knowledge, the NOGA mechanism can guarantee to converge rate by using CSAF approach. And cascade architect I will introduce in section 2, and then based on normalized orthogonal gradient adaptive algorithm, or we call NOGA, adaptive directional and negative gradient vector is an important key to make smooth and fast convergence. We'll introduce next. And then convergence properties and present some experiment results, and then conclusion finally. For this figure 1, proposed cascade by architect we connect with linear model, nonlinear, and linear model based on normalized orthogonal gradient adaptive algorithm should be introduced. Followed by this figure 1, this cascade model will comprise to LAF linear adaptive filtering and a nonlinear memory-less function in the middle. At the first box, the output will introduce in equation 1, and then the output of nonlinear adaptive filtering with at J index span can be expressed in equation 2. When the big D is a spline-based matrix. It's not that the weight vector works vector M works as an adaptive contouring vector to for the third order polynomial spline integration as shown in equation 3. And a local parameter as shown in equation 4, and then a position of index span J for nonlinear adaptive contouring vector is related with the output set output of the first linear adaptive weight. and a number of tab range P will introduce in equation 5. And then, therefore, the output here, the output Y, the output finally of second LAF linear adaptive filtering is given in equation 6. Then nonlinear problem, that is a big problem, is no apparent information in general knowledge. So that means the output error for figure 1 we will express in equation 7. Then for this section, we introduce an NOGA-based algorithm on Cascade by adaptive architecture by following previous work. So that means we will introduce you about cost function in equation 8. And then adaptive learning algorithm can be derived to minimize the cost function that shown in equation 8 that is based on stochastic gradient mechanism by computing the gradient with respect to the second linear adaptive filtering as shown in equation 9. Then for the adaptive contouring vector M is possible to obtain by equation 10 and by differentiate with respect to adaptive contouring vector M. For the derivation of stochastic mechanism for the first LAF, it is possible to compute followed by equation 11 with some alpha is a derivation of a vector A defined by equation 12. Then the proposed with vector W2 is linear adaptive filtering is block 2 of linear adaptive filtering based on NOGA will help to direction weight and gradient vector can be derived followed by equation 13 and 14. Then for the stochastic learning, the gradient for W2 can be obtained below in equation 15. Therefore, adaptive gradient can be performed by equation 16 and followed by some equation 17 to update it. Similarly, the proposed pi-based contouring vector can be expressed based on NOGA algorithm with the help of equation in equation 18, 19, and 20. So the gradient vector can be evaluated by equation 21 and 22. Then finally, the proposed linear vector based on NOGA and can be computed in equation 23 and 24. 23, 24, 25. And then for tuning value and forgetting factor for W1 can be defined by equation 26, 27, and 28. So for experimental result and discussion in this section, we will assume that the identifier of unknown CSAF architecture consists of 2 linear components with vector W2 and W1, and the 23 point of a nonlinear function of LUT length, followed by previous word. The input signal can be generated following in equation 42 with some constant something. And then for this experiment, we set some initial condition of a constant. Follow this by lambda is set at 0.125 and 0.725, and the signal to noise ratio at 30 dB is set for simulation. Fixed parameter for learning algorithm in experiment are follow this to test the algorithm. For figure 2, we compare simulation result of proposed NOGA-CSAF algorithm in the linear component. That figure 2 show the component of two linear adaptive in compared to equation 13 and 23 for the proposed. Then the results show that the proposed W2 vector W2 and W1 can update adaptively. For figure 3, we compare between adaptive spline vector and a target. This figure will show adaptive spline controlling vector compared with target. Then figure 4. Figure 4 is show a trend of MSE is mean square error curve of a cascade architecture when we set at lambda is equal to 0.125 of proposed NOGA-CSAF. Figure 4 is show that the MSE curve of cascade and architecture here compare with lead mean square conventional lead mean square CSAF in the different step size parameter average from only 100 simulation. It shows that the finally MSE is steady to lower than 30 dB. For this table 1, it shows average MSE in the unit of dB, the proposed NOGA-CSAF compared to conventional lead mean square CSAF. We show the average MSE of the proposed compared with this can demonstrate a better performance compared with our case shown in the table 1. Finally, in conclusion, the cascade architecture of spline adaptive filtering based on normalized orthogonal gradient adaptive algorithm have been introduced with some modification in stochastic gradient-based mechanism. And cascade spline adaptive filtering based on NOGA normalized orthogonal gradient adaptive is proposed also in the detail in the journal Convergence. Properties of the proposed NOGA-CSAF approach have been derived in terms of instantaneous error using Taylor series expansion. And then several experiments are conducted and tested in the nonlinear identification system to show for experiment results. The results of mean square error MSE curve clearly show that the proposed NOGA-CSAF outperforms the conventional lead mean square for cascade spline adaptive filtering in the case of underlying nonlinear identification system. So thank you for joining in this presentation.